Welcome to Summarize Science. Today, we're diving into a fascinating paper about a solar event that's challenging what we thought we knew about the sun's most energetic explosions. On July 16, 2024, the sun unleashed a peculiar, long-lasting blast of gamma rays. For over 7 hours, high-energy light poured from a flare on the sun's edge. This type of event is called a long-duration gamma-ray flare, or LGRF for short. And the mystery isn't just that they happen, but how they happen. For a long time, the leading theory was that these gamma rays come from particles accelerated by a giant solar tsunami, known as a coronal mass ejection, or CME. The idea is that a massive, fast CME plows through space, creating a shockwave that energizes particles. Some of these superpowered particles then rain back down onto the sun, smashing into its atmosphere and creating gamma rays. So, a big gamma-ray flare should mean a big, fast CME. But when scientists looked at the data for the July 16th event, shown here, they found a huge mismatch. As you can see in panel C, the gamma-ray emission, detected by the Fermi satellite, was intense and lasted for hours. However, the CME itself was surprisingly slow and modest, not the powerhouse everyone expected. Furthermore, a powerful CME-driven shock should also blast a huge number of energetic particles out into space, creating a major solar energetic particle, or SP event. But as these charts show, the particle storm measured by various spacecraft was incredibly weak. Here, you can see the proton levels barely rose above the background noise, even for spacecraft that were perfectly positioned to get hit. The particle storm was also very short-lived and didn't contain the super high-energy particles needed to explain the gamma rays. This evidence directly contradicts the idea that the gamma rays and the space particles came from the same source. So, if a giant CME shockwave wasn't the culprit, what was? The paper argues for an alternative scenario: giant magnetic loops. These incredible images show enormous, arch-like structures of hot plasma forming over the flare region. The researchers observed these giant loops, bigger than the Earth, persisting for the entire 7-hour duration of the gamma-ray event. The new theory suggests that particles get injected into these magnetic traps. Once inside, they are bounced back and forth, getting continuously accelerated to incredible speeds by turbulence within the loop, like a natural particle accelerator in the sun's atmosphere. Eventually, some of these particles leak out of the ends of the loops and hit the sun's surface, creating the long, steady stream of gamma rays. This loop model elegantly explains why you can have a powerful, long-lasting gamma-ray event without a giant CME or a big particle storm. So, let's recap the key points. The July 16, 2024 solar event is a perfect counterexample to the prevailing CME-shock theory for long-duration gamma-ray flares. The flare was long and powerful, but the associated CME and particle event were weak. Instead, scientists observed giant, stable magnetic loops over the region for the entire duration of the flare. This strongly suggests that these loops acted as particle accelerators, trapping and energizing ions locally in the sun's corona. This discovery could fundamentally change our understanding of particle acceleration at the sun, suggesting that these loops, which may have been overlooked, are a crucial ingredient for the sun's most energetic events.